Our next talk is our first remote talk, and also first now speaker, Bobby Wilson, who is also associated with the EDGE program and at the University of Washington. There's the title, Resonant Dynamics in Evolutionary Dispersive Equations. Over to you, wherever you are.
Thank you for the introduction, and I hope everyone can hear me. I tend to speak quietly, but if I begin to mumble or it's hard to hear me, just let me know and I can speak up. So I was lucky enough and fortunate enough to be a part of the first group of Karen-EDGE fellows, and which means that I was able to meet Karen for the first time in maybe like this spring, I think. So I don't have any like stories that you would, I guess, typically speak about at a birthday conference, but I can say a little bit that will be sprinkled in throughout the talk about interactions. But yeah, I'm happy to be here, or I'm happy to be invited. I wish I was there in person. Unfortunately, I couldn't make it. But yeah, I guess I should get started. What I would like to talk about is, as the title says, resonant dynamics and evolutionary dispersive equations, in particular nonlinear dispersive equations. And I think one of the things that I'll probably say is that I think Karen would maybe correct me to some extent and say I work generally in semilinear dispersive equations, not fully nonlinear dispersive equations, but we'll talk about that a little bit today. So in particular, I think what I want to focus on is how one extricates the nonlinear or the non-resonant types of interactions in a coupled system and a nonlinear system from the kind of resonant or the linear dynamics of that system, in order to kind of describe the dynamics of the full system by a simplified version or an effective equation or a resonant equation, or however you want to describe it. It was suggested to me by Karen to try to be as simple, well, not as simple as possible, but to try to make a simple talk. And I hope I didn't overcorrect, but we will start very, very simply with a simple harmonic oscillator, just so that we can establish some terminology and some ideas, some very basic ideas about what we'll talk about later on in the talk. So let's see if I can get this thing going. Okay, here we go. Okay, so yeah, like I said, very simply, we're gonna start with a very simple harmonic oscillator, and we're going to force it with oscillatory terms. And so again, very basic here. A is just some function in time with elements in C. And taking values in C. And we'll talk about a few different types of forcing. The first is what I call resonant, in the sense that the frequency of the forcing term, this oscillatory term, it matches the natural frequency of the equation, and it creates a type of effect on the dynamics of the system in general. There's a non-resonant forcing, which I describe as forcing with an oscillatory term that has a frequency that's very far from the natural frequency. And finally, nearly resonant forcing, which is when you have a term that has frequencies very close to the natural frequency. And in this case, the third is really the enemy. The first two are fairly easy to understand, but the third can be really difficult, and what typically people call well, I'll get to this in a second, but I'll just here I have the solutions to these different types of forced equations. As you can see, in the resonant forcing, you have a very different type of dynamics than you would in the case where you have the free equation. Instead of having something, the solution that just oscillates, you have some term that grows off to infinity as time goes to infinity. For non-resonant, you have a sum for non-resonant forcing, excuse me, you have a sum of two oscillatory terms, and in particular, the coefficient in front of the term that comes from the forcing is going to be quite small if omega is very big. And finally, for the resonant forcing or nearly resonant forcing, you're going to have the same term, but because you're nearly resonant, that term will be incredibly large. And what typically people call these things as small divisors, and maybe it's an obvious why in this case, because the divisor is very small. So here I just have a little bit of a more kind of analysis of what these things look like. And again, I'm starting very, very simply here, just to try to understand or try to establish what we're looking for in different types of nonlinear systems when we get to nonlinear systems. Again, I looked at the real part just to try to give a little bit more of a hint as to what's going on here. We have, for the non-resonant forcing, our coefficient is some small number, epsilon. And for the nearly resonant forcing, we have 1 over epsilon. And it's also important to note that for the nearly resonant forcing at time 0, you have no impact of that. But as time evolves, you have varying impact depending on which time you're in. And as time goes off to infinity, of course, this sine omega term and the real part of the free term will they'll become almost decoupled in some sense. They'll be very different from each other, or they'll be big in different times. So it'll become less of constructive interference and more not constructive. So again, just to establish some terminology here, we have, in the case of let's say non-resonant forcing, and in the free equation, we have this type of linear evolution, and in the sense that the solution looks almost like the original linear equation, the solution to the free equation. Then there's the resonant type of behavior, in which your solutions, your general solutions, look kind of like what the resonant solutions would look like. And in this case, maybe if you were to go back and say, instead of having just a forcing of the resonant term, but you had a forcing of the resonant term and a non-resonant term, or take the sum of a resonant term and a non-resonant term, you would still have this resonant dynamics because the non-resonant term wouldn't have much of an effect. And then neither. And so what I would like to do is maybe have one of my first oversimplifications here, and say that, generally speaking, if we have asymptotic behavior that looks like the linear evolution, then we call that scattering. And if we have asymptotic behavior that looks like the resonant evolution, then we call that modified scattering in some sense. Okay, so again, very, very basic. So let's try to make it a little bit more difficult. Let's consider, we're in finite dimensions still, but now we have a system of n simple oscillators. And we have a nonlinearity that couples the equations, and it's a little suggestive as well. This looks like a basically the cubic Schrodinger equation on the torus, but at the moment we just look at this cubic nonlinearity with a system of n oscillators. And the question we want to ask, again, for this very simple system is how do we identify the resonant, non-resonant, nearly resonant interactions in the same way that we did for the simple oscillator. And there are many ways to think about it, but I think maybe since we've already talked about the simple oscillator and we've already discussed what happens when you have a forcing that looks like an oscillatory term, why don't we do a type of iterative analysis and look at what pops out and see what we can say. So let's do that. So instead of just looking at the full equation, I'll consider a sequence of solutions to more and more difficult equations. The first equation we consider is just the linear term, and then we define a recursive system in which the next term is given, is defined, or you have an equation for the next term, the linear equation, with a forcing that is defined by the previous term. So instead of having some type of autonomous a system, it's actually, since we've already defined what the previous step is, it's actually non-autonomous because this is a function that we can define. And in particular, I don't want to go, so you can, one can now analyze this, all of the terms, or you can keep going and you can plug in and you can create trees of what happens when you look at different types of sequences of solutions. But I really want to focus on the first two steps. Okay. So, and I think that's enough to understand exactly what's going on here. So of course, the first step is just the sequence of or the n simple oscillators. But the second step, we start to see exactly what we saw in the very simple case. And that's, we have a linear equation or a simple oscillator equation on the left side, and we have this oscillatory forcing. Of course, it has some coefficients, but those aren't incredibly important at the moment since we're in finite dimensions. And we see that we run into the same, or we have a similar situation in that we can analyze, or we can compare the frequency of the natural, the frequency of the free equation, or the linear equation, with the frequency of the forcing terms. And in particular, what we get is linear combinations of these things. So in particular, whether we can determine whether the determination of whether one of the forcing terms, or one of the sum of the forcing terms on the right side of the equation, is resonant or non-resonant or nearly resonant, depends on what lambda k minus lambda k1 minus lambda k2 plus lambda k3 looks like. It's completely determined by this. Okay, and so you have a kind of, I guess, a dichotomy in some sense, I suppose, or in that you have resonance when it's equal to 0 and non-resonance when it's not equal to 0. Okay, and this is just to give a little bit of motivation for what we'll talk about next, when we actually add some a little bit of structure and formalism to what we're discussing here. So let's do that. And one thing to note, I suppose, is that since there are so many forcing terms, you could end up with a lot, and especially since we're dealing with only finitely many frequencies, we can end up with a lot of situations in which this linear combination of frequencies falls between being much bigger than 1 and being very close to 0, right? Or being 0, in fact. And so what do you do with these in between nearly resonant interactions? Typically what you would do is simply go to small data, which is will be a theme in this talk as well, which you just add an epsilon, and all of a sudden there's an epsilon in front of all of the terms, or an epsilon cubed. Okay, and so that then the non-resonant, non-resonant meaning those that are actually very, very far from resonant, and those that are actually nearly resonant. And the non-resonant terms are mollified regardless, because you have this extra epsilon cube term. Okay. So again, it's very, very, very simple. So let's talk a little bit and add a little bit of formalism to this, and speak a little bit about, and try to lead up into what we want to talk about, which is PDEs. Just to give, I guess, again, to establish some notation and establish some terminology, we consider a symplectic structure, symplectic structure on C2N, and we consider the previous equation that we were looking at as a Hamiltonian, or a Hamiltonian equation. And its Hamiltonian is given by here, by this, and then we can define non-resonance pretty clearly, or pretty, I suppose, specifically in this case, as essentially linear combinations of your frequencies not being 0. Okay, which is again what we kind of saw in the previous analysis, that if we had if we did at least the iterative or the recursive formula, then what determines whether we have resonant interactions or whether we do not is completely dictated by what the linear combinations of the frequencies are. And of course, in this case, non-resonance is asking for a little bit more than you would necessarily need in a given case, because it's asking say, that any linear combination of your frequencies is never zero. And in particular, in general, you're only dealing with certain linear combinations. But regardless, if we really want something strong or a very strong condition on our frequencies, then we say any linear combination, of course, any linear combination that's not too big will lead to non-zeros. Okay, and then normal form I have here. Again, I think we will probably not need this terminology too much, just to remain, I guess, simplified in this discussion. But the normal form is essentially equivalent to saying that, or the fact that your let's say your polynomial here p, or your function p is a normal form is saying that these linear combinations are equal to zero. And so so you don't have any non-resonant terms. If you do have any terms, they're all resonant. Okay, let's see. First theorem is a question of what to do. And again, I mentioned before, what we would like to do is understand how to extract the resonant or the linear behavior from a system that has a that has a linearization, a nice linearization, but also has some nonlinearity added to it, and a nonlinearity that's generally speaking a perturbation, or in most cases. And what we have here is the first example of that. And again, this is in the finite dimensional case, and we'll move to the infinite dimensional case once we finish this discussion. And we have, again, the quadratic part of our Hamiltonian. We have a function that has 0 order 3 at the origin. And basically what we can do is we can find a change of variables, a nonlinear change of variables, that allows us to eliminate all of the non-resonant terms. Okay, and the non-resonant terms are the terms, generally speaking, we expect to not have a large effect on the dynamics. We can eliminate the non-resonant terms, and all we're left with are resonant parts plus, unfortunately, plus an error. Okay, and so then the resonant terms are the Z term, and the errors is R term. And so this R term is going to be of higher order, and of course, if you have well, okay, we'll talk about that. But generally speaking, it's as high as you want it to be if you choose it at the beginning of your process here. If you say I want to have an error of order or degree m or m plus 1, then I can find some nonlinear change of variables. Of course, you would, generally speaking, like to eliminate the area, but this the error, excuse me. But this would require, in most cases, infinitely many of these, compositions of these types of nonlinear change of variables. Let's see. Yes. So what am I saying here? And I think, yeah. Okay. So we have Z as the resonant part, R as the error, and of course error only if you're in with small data. And this is going to be a big theme, that the analysis will often require that we assume that we're in a small data regime. And we also have that the final bullet point there is that the change of variables is close to the identity. But of course, this again requires, as you can see, the errors is degree 2 or order R2. It requires small data for this for anyone, or for you to claim that this is close to the identity, of course. Okay. And okay, before I come here, I want to say that it's important to realize that what's missing from this, the beginning of this theorem, there's no condition on whether or not you're resonant or not, or your frequencies are non-resonant. And so you can do this regardless of what the resonant or non-resonant properties of your frequencies are. But if you do have some non-resonance condition, then you can essentially eliminate your z term. Not essentially, you can actually eliminate your z term. And then you only have the error. So you don't even have to analyze the dynamics of the resonant equation. You can simply say that I have, after a change of variables, I have my quadratic part of my Hamiltonian, which is a linear part of my vector field, plus an error that is of arbitrarily high order. And in that case, I have this nice stability. Okay, so let's finally move, I think it's time to move to infinite dimensions. And I'm looking at nonlinear Schrodinger equation here. And again, as I mentioned before, Karen reminded me that since my target is C, and I'm typically looking at a polynomial nonlinearity, I'm really in a semi-linear case. And so she graciously offered to talk to me about actual nonlinear Schrodinger equations when I visited, and that was pretty nice. And keeping with that, I think I'll make a little bit of a adjustment here. I'll change that to semi-linear Schrodinger equation, and I'll actually look at, in particular, the cubic equation. All right, so what we like to do for the moment is try to go from finite dimensional changes of variables, finite dimensional resonant dynamics, and of course, and resonant analysis, and then one-dimensional resonant analysis to infinite dimensional analysis. And so what does one do? I have an example of what a non-resonance condition could look like in the infinite dimensional case. Of course, the issue with infinite dimensions is that you may have infinitely many frequencies, distinct frequencies. And of course, this can be, what the difficulty is that if, in the case that you have finite dimensions, there is a minimum non-zero linear combination given a finite control or some control over the length of your linear combinations. And for infinitely many frequencies, there's no such thing, of course, because you have infinitely many frequencies. So you have to deal in some sense with these arbitrarily small, possibly arbitrarily small divisors. And this is a humongous problem, essentially. It breaks a lot of what you would like to do in this area. And I have a very simple example here. It's a pretty weak condition, and in fact, it's weak enough that it actually doesn't allow for the theorem that I'll quote next. But essentially, what in this case you can say is that I know that I have infinitely many frequencies, and what I would like to do is say, well, cut off at some n, and assume that I only have interactions between frequencies up to n. I would like to say that I can control how far away from zero that is. And in particular, I have a control over how far away from zero is. In the previous case, we had no gap between what the smallest linear combination was and zero. In this case, we actually need it, because if it's arbitrarily small, or if it's increasingly small, or if this if the size or the smallness of the linear combinations can go to zero exponentially, then we're in really bad shape. We can lose a lot of regularity in our normal form transformation, because we're looking at an infinite dimensional transformation on a Hilbert space. We could end up losing regularity, and which messes up essentially everything. Is if you want to show some type of well-posedness, if you want to show some type of dynamics, then losing regularity can be very fatal. And of course, in some cases, it's not so bad, in particular if you want to show existence of solutions. But if you want to show something like for general solutions or general small data solutions, then it becomes a humongous issue. So this is an example of a non-resonance condition in the infinite dimensional case. Generally speaking, you must account for the possibility of interactions between relatively low frequencies and arbitrarily high frequencies, but in this case, for simplicity, I left that out. Okay, this is a lot, but I think that I want to point out here is that it's essentially the same thing as the Moser theorem, but it's in infinite dimensions. And I should also point out that this is not 2006 Bambouzy-Grobert is not the first normal form theorem you have in infinite dimensions. That you can go back to Chatat in 1985, but it's the one that I'm most familiar with. So I gave this as an example. But it looks more or less very much like the Moser theorem, and it's essentially you assume you have a non-resonance condition, one that's stronger than the one I quoted before. You have this local transformation, local change of variables in some Hilbert space that whose regularity is dependent on this, or is determined by this S number. And given that, you have a normal form transformation, and you have the resonant part, this Rm, and then you have the error here. And again, because you have this error, you're assuming, in order for things to be relevant, you're assuming that you have small data. And again, you have some type of control about of how close this nonlinear change of variables is close to the identity. And I will point out again that you need, I maybe am repeating myself too much. You need small data in order to call this close to the identity. And then the similar bounds to before, you have an error with the high degree, and that. So I want to discuss some applications of this type of change of variables before I move on to another way of extracting resonant information from a nonlinear system. And I should note that these examples of applications is not exhaustive. There's a lot of stuff that I'm going to that I have not included in this slide, but it gives, I'm just trying to give an example of what things can, what one can show. And the first is of course, if you're on looking at NLS on the torus, or the d-dimensional torus, you have a special set of solutions that are periodic. And one can ask essentially what the stability is around these periodic solutions. And one can use a normal form transformation to show that you have arbitrarily a long time stability. Moreover, if you look at the cubic NLS on the square torus, and in keeping in mind, I think, and it's a result that I'll mention later. Keeping in mind there's a little I-team about instability and weak turbulence for cubic NLS on the square torus. Carlos and Fau are able to show that with a nonlinear change of variables, you can get a little bit more quantitative information of what how the frequencies behave over short times. And then in this vein, I, along with Saflani and Hrabsky and Pan, we looked at what happens if you rescale the torus so that the frequencies are a little bit different, and they exhibit a different resonant structure. And I would be remiss if I didn't talk about what's happening a lot now lately with water waves and things like that, and in particular, normal form transformations can be very helpful when analyzing systems in which you don't have very nice well-posedness results. And in particular, these are a few of the large body of work. And again, I have to apologize because there's so much work, and there's so many people, and there's such a large body of work in this area that I couldn't do it justice on during this talk. Okay, but in particular for constructing solutions, and for also showing the long time existence of solutions for, again, small solutions. So let's talk a little bit about benefits and shortcomings of looking at this. And I've maybe harped on it a little bit too much so far. The normal form theory, the resonant systems are obviously a little bit easier to analyze. If you look at arbitrarily small data, then the resonant system is really what dominates. When one issue is that the change of coordinates is local. So if you want to show something for infinite time, then this is not really the way of going about it. And arbitrarily small divisors are difficult to control. And even that being said, in order to control them, typically you have to pass to a subset or a sub case in which you're in the regime that you're considering. So let's move on to a different type of argument. That's again a way to separate resonant dynamics from the rest. So in this case, I'm looking at essentially, in my mind, nonlinear Schrodinger equation after, let's say, a gauge transformation. And I'm splitting the nonlinearity into a resonant part and then a non-resonant part. The resonant part is R, and the non-resonant part is E. And then I'm considering a solution to an effective equation, let's say, in which there is there's no non-resonant part. And the idea is that when you look at the difference between the flow with respect to the resonant part and the flow with respect to the non-resonant part, you should be able to look at the dual term that you were given for the non-resonant part and show that there is some cancellation in this dual term. And that cancellation is enough to say that the effects of the non-resonant part are small compared to the effects of the resonant part. And this is exemplified by this inequality. Epsilon of t is going to be small or going to 0. And this is probably a gross oversimplification of what you would typically do in this situation. But I wanted to make it fairly simple here of what people are essentially doing. And yeah, and it's and I mentioned here that you sometimes use circuit system and things like this. So it is much more complicated than it appears to be just on this slide. So I'll give in a couple of examples, and I mentioned the first theorem before, but a couple of examples of what we can do or applications of doing this type of integrative method, where you don't do a change of variables. You look at the resonant part, you look at the non-resonant part, you do a gauge transformation, you integrate both, you use maybe some integration by parts, you use some strict rates estimates, and you show that the non-resonant term is simply, it's not as important to the long-term dynamics as the resonant terms, just by establishing an inequality. And what you can do is what the I-team did in 2010, in which they demonstrate that you have this type of what they call weak turbulence, where small solutions can grow arbitrarily large. And this is again by analyzing and demonstrating that you can show growth in the resonant equation or the effective equation. And then from there, you can show that the non-resonant part is not important. And then I should also mention this result of Guattari and Koloshin, in which they show that they do a quantitative version of this. And for small data, actually, they have a better bound for the time. Okay, so I'll mention this, and I should be quick here. One important part of the resonance analysis is showing that you can construct these families of resonant interactions that allow your Sobolev norms to grow. And this is a long-winded proposition, but I just want to compare it to the next. And I suppose I should mention a little bit here is a sequence of subfamilies in which energy essentially transfers over time. Energy transfers from lambda 1 to lambda n, and so in particular, your Sobolev norms given by the weights here, or I guess simplified by just considering the weights here, they must grow to some extent. And so if you change the torus and you change the frequencies, the resonant structure changes as well, as you can imagine. And in particular, if you look at an irrational torus, the resonant structure changes so much that you cannot create these families that grow. Okay. So what does this mean? It means that you can't go about the same construction using the resonant equation, but you do have this weird thing that when you change these frequencies in the way that you do by changing the rescaling the torus, you still end up with many, many almost resonances. And this is really the danger and the the heartache that you can encounter when you're looking at resonant or when you're trying to establish resonant dominance over the dynamics of a system, is that if you have arbitrarily small divisors and you have arbitrarily nearly resonant interactions, then they can influence the dynamics of the system so much so that they almost look like their resonances, essentially. And this is basically what this proposition is saying, that in the case that you, although you do not have the structure to construct this resonant dynamics that allow for growth on the resonant or the effective equation, you have enough almost resonances to get the same type of growth, although it takes a little bit longer. Okay, let's see. Cool. All right, so I'll talk, okay, briefly about infinite time as well. These are all finite time results. So it's up to, they're not asymptotic. So what can you do asymptotically? And you can use this type of integrative method for asymptotics, in particular for scattering. And again, this is a very small subset of the people who have worked on this. But you know, I want to keep this short. So, so I chose a few particular references to allude to, and I also wanted to talk a little bit about what happens if you try to do the same type of non-resonance or changing the resonance structure in the case where you have a, let's say, a mixed space in the case I have here. But these are examples of situations because you are in a non-compact manifold, you do have a modicum of dispersion. And so when you integrate your non-resonant term, you can actually integrate from 0 to infinity, not just 0 to t. And this allows you to, again, say that, okay, over asymptotically, I can say that my dynamics are resonant, not just over some short amount of time, but asymptotically. There's a long story here that I'm skipping over, but this is essentially the idea that you study or you integrate, and then if you have enough dispersion, if your Stricker estimates are good enough, then you can, as I said before, you can extract the resonant information or the dynamics of the resonant system and say that, okay, the full system displays this type of modified scattering in which you look like the resonant system. And this is what the last reference here is doing, essentially. In the case where you're in R cross TD, you use constructions given by the I team to show that you have this type of modified scattering. And then I mentioned something recent where my collaborator and I, we looked at the same type of thing, but again, changing the resonance structure so that you have many small divisors and many nearly resonances as opposed to resonances. And in this case, when you have some modicum of dispersion, you're able to to some extent mollify the effects of the small divisors. And sorry, I'm not going very in depth in this, but I wanted to cover a lot of things. And so let me talk a little bit again about benefits and shortcomings of the integrative approach. You can, of course, eliminate the asymptotic dynamics. This is very, very nice. Of course, in the normal form case, asymptotics are out of the door because you have a local change of variables that doesn't necessarily give you information about what's going on long term, of course, unless you can prove that you stay inside this neighborhood or this neighborhood of small data for all time. But in that case, you're in the best case scenario. In case scattering analysis, the resonance system typically sometimes is not necessary, of course, if you have scattering. Another nice thing is that you don't have higher order terms to deal with when you're looking at change of variables in normal forms. The Error terms, again, if you assume that you have small data, it's going to be small, but it's still there. And so if you want to say something about something that's not small data, then you're kind of you're out of luck to some extent. So when you look at the integrative approach, you don't have to deal with these. A shortcoming is that you do require strict cost estimates in most cases, which can constrain the dimensions that you're in. So if you're looking at d-dimensional torus, or you may have to reduce yourself to two-dimensional torus or three-dimensional torus. And moreover, if you're in the compact setting, it's less useful as well. And the non-compact setting, it's fairly nice. You can still lose some regularity when you're doing integration by parts arguments, and you often need small data, but not always. So the last 2 minutes, I want to talk about what happens if you are very clever, if you in fact would like to understand long-term dynamics, short-term dynamics, but you don't want to have to do some type of I don't know, surgery essentially on the on the vector field and the Hamiltonian. You can be really clever, and then you look at inverse scattering. And I'll just mention this. Yes, I won't spend too much time on this, but and I'll give a very kind of oversimplification of the way in which one looks at this. But when you, so I guess generally speaking, when you're looking at, for example, cubic NLS, you pass to a you pass the Fourier coefficients. You are essentially diagonalizing, or you're using the coefficients that diagonalize your linear equation. And although it does simplify things to some extent, in many cases it doesn't simplify enough to be worth it. And so what you do in inverse scattering is simply you diagonalize with respect to the full equation, and that's in a talk with a lot of gross oversimplifications. That's probably the grossest oversimplification of what inverse scattering is, but this is the way that I kind of understand it. So in particular, if you and I give the example of the KdV equation because it's easier to write, but you're looking at a solution and you're looking at a Schwartz function, and again, you're on KdV and you're not periodic, and you're looking for eigenfunctions for the Schrodinger operator and eigenvalues and eigenfunctions, and they're adapted to solutions. Here, your U solution is a solution to KdV in this case. For this example, you can do this for NLS on R or NLS on a torus, but you get like a matrix, and it's a little bit grosser to write. The gaps between the frequencies of these of the Schrodinger operator provide you constants of motion, which is, to me, it's kind of amazing and mysterious, and I've been trying to understand it for almost 10 years now, and I don't know, I think I'm maybe 10% of the way. But yeah, it's a fascinating subject. And then from there, once you've done this, once you've shown that these are constants of motion, once you've I guess discovered the lax pair, then you need to demonstrate that the constants of motion are actually allow you to put your equation in action angle coordinates, which is essentially that even though you may have found infinitely many constants of motion, you actually have to show that it gives you, in some sense, a foliation of phase space. Because you are infinite dimensions, you could have half as many as you need. So you actually have to show that you have actual action angle coordinates. And I'll finish with just an allusion to I think tomorrow's talk about what clever people do when they want to understand dynamics of Schrodinger equations. And I'll mention the work of Uhlenbeck, and I have to say that one thing that helped me a lot when trying to understand what they do is a article by Richard Pillay, in which describes a little bit of inverse scattering and what Turing and Uhlenbeck do. And the sparseness of this page, it's reflective of my 10% knowledge of what's going on in in inverse scattering and integrable systems. So, but that being saying, this is I guess the point I'm trying to make here is that in the case of doing local analysis with normal forms, or trying to do long-term analysis with integrative methods, you have pros and cons. And if you are lucky enough to be able to analyze it from an inverse scattering perspective, then you can get almost a complete description of your dynamics, not only over a long time, but locally as well, and locally and globally. So globally and in phase space. And so it's really great, and I hope to learn a little bit more about it tomorrow in the talk. But I think I'll end my talk here. Thank you for listening.
Thanks very much. We have time for one or two quick questions.
I always like to say something here. That was a very nice talk, very good at explaining to people who do non-linear elliptic PDE why nothing that you do in nonlinear elliptic PDE carries over into studying the types of equations you're talking about. Because do you have a comment about that? I mean, somehow or other, you never get nonlinear elliptic PDE. Somehow you even get to use implicit function theorems and things. You know, it starts to look like calculus if you do it right. But there seems to be no such way to do this for these dispersive equations. What would you say? Do you have anything to add to that? Is there, we of course start with ODE, which we understand, but is there any quick way to get any intuition for the subtleties? I mean, I'm still bewildered by the difference between I've not heard anybody talk about this, and I always want to ask the question, the difference between the irrational and rational tori.
Yeah. So yeah, on the first point about going from finite dimensions to infinite dimensions, yeah, a lot of it you study it and then you realize that you're trying to generalize something that's in finite dimensions, but you're somehow trying to fit infinite dimensions in finite dimensions. I think that's really the where the difficulty comes in, is that you are really trying to use a finite dimensional method for something that is infinite dimensional. And it's okay in certain cases in which you control how bad infinitely many interactions of waves can be. And in some cases, like for example, if you have a little bit, if you're in R, let's say with Schrodinger's equation, you have some dispersion, and so it allows you to some extent say that my wave packets over time they're going to, even though they interact with each other, there's going to be less interaction over a very long time because they have a different they're moving away from each other to some extent, even if there's some nonlinear interaction that I've given it. But even then, you still have to control the error. And and it's not simple, and you have to do it over a long time, and you have to have some heuristic that is finite dimensional, and maybe even if you've extricated these different packets and said, okay, I have these different things and they're completely separate, but now I have to analyze each of these as a finite dimensional system, and now I have infinitely many finite dimensional systems again. I have less coupling, but there's still many of them. And so yeah, non-resonances, the non-resonance condition that I gave before is one way of doing this. The infinite dimensional one, but it's not enough. I mean, if you have interactions, you have interactions. If you have interactions between low frequencies and high frequencies, there's nothing you can hope that things aren't so bad. but there's nothing you can really do. And so you also asked about the irrational torus and the rational torus. I think the best way to think about it is simply, I'll leave this non-resonance condition up. So in the rational torus case, your frequencies or your eigenvalues for your Laplacian, they're all integers. And what happens for the irrational is that you rescale it so that instead of integers, you have things that are not integers or perturbations of integers. And so what does that mean? That allows you to do is play some games essentially and say that I can pick the right, or I can pick many different rescalings, irrational rescalings, so that I don't have the same type of resonant interactions that I would have in the rational, the square case. Okay, so that means that I have less. And so in the cases where I had, n squared plus n1 squared minus n2 squared minus n3 squared, that's equal to 0. Now I rescale it a little bit. Now it's not equal to 0, which is great because now your resonant system is simplified, but it's probably close to 0. So, and before in the case for the square torus, if it's not 0, it's greater than or equal to 1, your non-resonances. And so you don't even have small divisors in some sense. And so you eliminate some problems by making your resonance system simplified, but you introduce a whole host of problems that you find in waterways, for example. This is something that people are dealing with, and simply because the dispersion relation has a power that people aren't used to dealing with. It's like it grows like a square root as opposed to squared, and so yeah, I think. Yeah, I think that's my kind of understanding of how these things work.
Well, I think we'll have to defer further discussion on this interesting topic to online and on the cloud. So let's thank the speaker again.